Well, now that we know what u is, we can put our u back into its e value, because ultimately we need to find what x is, not u is. So I'm going to replace my u back with e to the power of x. When I do that, then I can get x by itself by multiplying each side by the natural log, since we know that the natural log and e will end up canceling themselves. I can use my power rule. I also know that the natural log of e is just 1 itself. So x times 1 is simply x by itself. And now I have two values for our x. We have the positive value of 3 plus 2 square root 2 and 3 minus 2 square root 2, giving us two approximates of 1.76 and negative 1.76. If I wanted to solve this graphically, since it's already set equal to 0, we could use the zero graphing method. By saying y is equal to e to the power of x plus e to the power of negative x minus 6, and find where our graph crosses the x-axis, where the zeros are located. And we would see that they would cross the x-axis at 2 locations. Our next example, it says to solve the log base 3 of x is equal to negative 2. Our goal is to try to obtain a single log expression. So right now I have log base 3 of x is equal to negative 2. Well, I know according to my, if I were to write this in exponential form, I would have my base 3 to the power of negative 2 is equal to x. I know that I can bring this down into my denominator to make it positive, giving me 1/9 is equal to x. Of course, we can check. So if I were to take log base 3 of 1/9, I would see that I would have 1 over 3 squared, which reversing gives me log base 3 of 3 to the negative 2. And since these are the same using our properties, I would have negative 2 equals to negative 2. So this gives us a true statement. So the solution is 1/9. Probably a few too many steps needed there, but let's say I have log x plus log of x plus 3 is equal to 1. Using my product rule, I see that our bases are the same, and I'm adding, so I can bring them into one value, giving me log base 10. Again, if we don't see a base, we assume it's 10, of x times x plus 3 is still equal to 1. Using our exponential, so we're going to write as an exponential. I can take my base 10 to the power of 1, so 10 to the first power equals all this stuff. I can then distribute my x values, giving me x squared plus 3x equal to 10, since 10 to the first power is 10. I'm going to set this equal to 0, so I'll subtract 10 and bring it to the left. And now we can factor by finding two numbers that multiply to negative 10 and add to 3. see, positive 5 times negative 2. So x minus 2 and x plus 5. Setting them each equal to 0, we get x minus 2 is 0, or x is plus 5 is 0, giving our two solutions as x is 2 or x is negative 5. Of course, we have to check our work because we know sometimes that they don't always work. So let's check 2 first by plugging in 2 wherever we see x. That gives me log of 2 plus log of 5. Again, we're adding so we can multiply our of pieces together, giving me log of 2 times 5 or log of 10. Right, 10 to what power gives me 10? We know that's the first power, so this is true, so 2 is a solution. Let's try for negative 5. So log of negative 5 plus log of negative 5 plus 3. Oh dear, we have a problem. We can't find log of negative 5 because it's not in the domain. So negative 5 cannot be a solution because it's not in the domain. So our only option is 2. If you wanted to solve this graphically, we would set y equals log of x plus log of x plus 3, and a second line of y equals 1, and find where the left-hand side and the right-hand side intersect. So we would solve by the intersection method, and we would see they would intersect at x equals 2, based on the solution we found algebraically. Few more to go. Let's solve log base 3 of 2x minus 1 minus log base 3 of x minus 4 is 2. So I see we're in subtraction. So, and we have the same base. So I can rewrite this using our difference rule. That would give us division, giving me log base 3 of 2x minus 1 over x minus 4 is equal to 2. Now to get rid of the log base 3, I write my base to the power of 2, so 3 squared is equal to the left-hand side. I know 3 squared is 9. My goal is to get our x value by itself, so I'm going to multiply each side by x minus 4 so that I can eliminate my denominator, leaving me with 2x minus 1 on the left, and then I can distribute 9x minus 36 on the right. I can combine some terms here, so I'll add 36 and subtract 2x, giving me 35 is equal to 7x. So when I divide by 7, I see that I get 5. Of course, we should double check because as we saw in the last example, perhaps an answer may or may not work. So wherever I see x, I'm going to plug in 5, giving me log base 3 of 10 minus 1, or 9, minus log base 3 of 5 minus 4, which is 1. 3 to the power of what would give me 9, so that would be 2. 3 to the power of what would give me 1, well, we know anything to the 0 power is 1, so 2 minus 0 is 2. We get a true statement. We could solve this using the intersect method by setting this side equal to y and the right side equal to y, and deciding where they would intersect one another. Let's try another one, except this time we're going to use the natural logs. I have the natural log of 4x plus 6 minus the natural log of x plus 5 equals the natural log of x. I see I have subtractions, so I know that I'm going to be able to divide them. Give me the natural log of 4x plus 6 over x plus 5. equals the natural log of x. We have a fact that if I have the natural log or a log and the bases are the same and they're equal to each other, ultimately these parts disappear. So I'm back in page 1 of our notes, leaving me with 4x plus 6 over x plus 5 is equal to x. Just like in the last example, I'll multiply each side by x plus 5 such that I can get rid of our denominator. I can also distribute. So x squared plus 5x on the right with 4x plus 6 on the left. Getting everything together, setting it equal to 0 so that we can factor. I have x squared plus x minus 6, so now we can factor by finding two numbers which multiply to negative 6, but yet at the same time add to 1. Let's see here, 3 and negative 2. So I have x plus 3x minus 2. Solving each one would give me negative 3 and positive 2. Well, we know that negative 3 cannot be a solution because it's not in the domain. And if we were to double check, 2 would be the value that would work. We could also solve using the intersect method by setting the left-hand side equal to y and the right-hand side equal to y and identifying where they cross where they cross each other. And our last example, another example using the intersect method. So I'm going to switch over to decimals as I explain through here what we're doing. So within decimals, we're going to talk about the intersect method and the zero method that we've been talking about all through our notes so we can see what it looks like. It's asking us to solve using the intersect method. So on the left-hand side, I'm going to enter in the y equals e to the power of 0.5x minus 7.3. And on another line, I'm going to say y equals 2.08x plus 6.2. And I'm going to make my screen a little bit bigger so I can identify where they cross one another. So there's two locations with which they cross each other. When we graph these equations, we see 2 points of intersection. If we click on the 2 places where they intersect, the first coordinate of the points of intersection are the solutions. So our solutions are approximately negative 6.471 and 6.61. We could also use the zero method to do this. In order to use the zero method, we have to have our entire equation equal to 0 and only have one y equals value. So I'm going to get rid of this second one, and I'm going to start with this e to the negative 0.5x minus 7.3. Then I'm going to subtract over the 2.08x and subtract over the 6.2. This time I see two locations where our graph crosses the x-axis or our zeros, and we can see that we obtain the exact same solutions that we did using the intersect method. Either one of them are just as efficient in solving.